So our regular expression will come into this file, and depending on what we enter in, it will seek out the specific characters we enter, and then there are other characters used to give directions to pull out the data that we want. So we begin with, in quotation marks, where am I? So here we begin with quotation marks as to tell Python to take what is in the quotation marks as a string. And then we begin with 2 backslashes and an asterisk. And this tells, our regular expression says to ignore everything you see before what is entered next. Like jump right to it, speed ahead, and it's going until what we enter in here, which will be at ID equal to online DDB-form. So it'll cut right ahead until we have our online DDB form, which if you look in here, I'll highlight it for you. So as you can see, right before this page starts, and this would be where all of these displays start occurring, we have our online DDB form, so it'll jump right past all of this and go right to where we need it to begin its analysis. And then, oh, I'm supposed to be inside there. The backslash will tell the regular expression that was the first, like this is the next step. So for the next step, we're looking for div 2, and if we take a look in here, there's these divs that happen, the divides that happen between different sections of the data displayed on this website. So after the second division, we'll be getting our table, and it's the third table in the setup here of 1, 2, 3. So back over here, the next step will be table 3, and then from the table body, you can see here in the different divisions, then it brings us to the table body right here in each table, and then within each table row, and then we have these TD values, which is going to be what we end up trying to pull, since this ends up being the third table body, TB3, or table 3 T body, sorry. And then within each TR, they're giving us the TD1 and TD2 will correspond with our temperature as TD1 and pressure as TD2. So back over here, our next command will be TD1, since this is the temperature strings. And from here, we want to pull the text. So this will operate as our regular expression. And then we want to do the same thing for our pressure values. And going through this way, it'll pull them in order down the site because that's how they're entered in. And we'll have our temperatures with the corresponding pressures each as like the first value in each array, or each list will be corresponding temperature and pressure all the way through the nth value in this list or in each list. So we have tree.xPath, and then we're going to copy our regular expression down into the bottom, and then the only change necessary is we want the second TD value, which would be our pressure. So now that we have both of these, I'm going to run it, and let's see. And as you can see, this is the list of all the temperatures pulled out of the Dortmund data bank in order, and these quotation marks that you're seeing indicate that these values are saved as strings. So now we can make a new variable called data, which will be our data with like each temperature and pressure. And then we want to save it as an array so that we can use it in our functions, and then temperature will be the first value, and then the pressure. Oops. Okay. And then we save as type. Because these are string values, we need to convert them into floating number values. So as type float 64, because we want the extra precision for these calculations. All right, and that should get us there. I believe I need to have a set of brackets around here. And, oh, I see what I'm doing wrong. It should be np.float64 because it's a numpy command. Okay, now it's working properly. And okay, so now we have our data pulled from the Dortmund data bank. We can do this, and now that's not looking so right. Oh no, I see. It converted it into scientific notation because we're using float64, so it's expressing it too as far as it is able to. Okay, that looks as it should. We have 293.15 degrees Kelvin here, corresponding with 2.4 kilopascals, and then our last value is 647.09 Kelvin and 2,133.6 kilopascals, 2,133.6 kilopascals corresponding with 647.09, and our temperatures and pressures match. It pulled everything properly. So now we want to put these values in a form where it would be appropriate to graph them. And when somebody is graphing this relationship between pressure and temperature, and this temperature is in Celsius, but that is a constant value change between the two. It's a scale up from Kelvin, or a scale down from Kelvin by a factor of 273.15, which would just act as a shift along the x-axis. It would not affect the scale of our display though. And this is what we would expect to see. We have the pressure in kilopascals and our temperature in Celsius. So T is our temperatures, and it's equal to the first entry in our data. So the way Python works is we're looking at our data, our first list of entries, the first column in this array is denoted as 0, the second being 1, and our first is our temperature values, our second is our pressure, so here we have temperature. And then we can do the same thing for pressure. But instead of adding a 0 there, we'll have a 1. And we want everything in the first, the second row, with all the pressure data being pulled out. All right. And now we want to create a plot to display all of this onto. So we'll create a figure. The fig will be the name of our figure, and use the command make subplots to, we have 1 row and 1 column, and this will just produce 1 subplot, as opposed to you can have multiple different subplots displayed across the same figure, but we just want 1. And then we want to add our data, so we'll use the command add scatter to add our data points collected from the Dortmund data bank onto the subplot. So x is equal to our t variable, y is equal to our p variable. We want to have this displaying our data points as markers. And we'll name this, the plot will be named data points. Or that'll be the name of these data points added on. That's what the key for this scatter plot will show them as. Okay, so I should be using this pressure on a logarithmic scale because of the way it increases with rising temperature. It increases logarithmically, so for a proper analysis, we should look at this across a logarithmic scale. So log p is equal to, and then we did not convert this from kilopascals to pascals, which was the original intention when we looked at here we wanted it in Kelvin and pascals on the Wikipedia page. So we'll use the command np .log10 of our data, but we want to convert it to pascals, so 1000 times the data. So this will be the log base 10 of our pressure measured in pascals. All right, and now I would like to shorten the width of this as well. So we'll do thing update layout, and then with the updated layout we're going to add, we can add axis titles as well to denote what we have in each, what units we're using for each axis. So we'll say axis title is equal to temperature and run the scale of Kelvin. And then y axis title will be set as, you add dollar signs to allow this to be written as a equation rather than being like a block of letters. So I will show what I mean by this in a second. I forgot to put in these quotation marks, so we'll cut this out, add the quotes, paste it back in. And then we also want to set a width of, I'll set a number and see how that looks. And that looks much more appropriate. So as you can see here, we have a log base 10 of our pressure. And then we have it in, that does look, I have the backslash and it should be a forward slash. Okay, there we go. And as you can see, we have a significantly increasing pressure. The boiling point of water we know is 100 degrees Celsius, so it would be around 373 degrees Kelvin, which would be right around here where the vapor pressure diverges from 0. This does make sense, and then it increases exponentially with increasing temperature. And I would just like to make sure why is my graph looking invert? see these log p values. So our highest value being about 7. Oh, I see my mistake because I did not change the variable here, so we weren't actually changing anything, and this should make quite the difference. Okay, now this is more I expected the curve to show. That looks proper. Okay, and then now we're going to want to define our Antoine model, and we haven't looked up the constants a, b, and c, and we should not need to for this. The SciPy optimize minimize function should be powerful enough to fit this equation to our data points. So we'll begin by defining our model, and it'll use variables a, b, c, and t. So return, and this will be the model of our log base of the pressure. The log base 10 of the pressure value is what this equation is returning. And the equation is, as we can see right over here, a minus b over c plus t. So a minus b over c plus t. And that is our Antoine equation. So no error defining that function. We'll go ahead and make guesses for our A's, B's, A, B, and C, just because it needs a starting point. You need to enter at least some guess for a starting point. And I believe it shouldn't really matter what we enter in, so I'll enter 100 for all of them. I could have just highlighted that as well, but here we are, and then we're going to save these values into a new variable, and this list will be x. And when we save, we save these a, b, and c values in here, and that's going to convert how we call on them. So where we have it defined with a, b, and c up here, we're going to need to call on them as x0, x1, and x2 to call for the first, second, and third entry in this list x. All right, so now we will define our square error. So for this, we can do a sum squared error to minimize our Antoine equation and fit it to the model to see how well it fits with this experimental data. And to do that, we would need our x, which contains our guesses, our temperature, and our pressures. We'll have our model P. And now doing this, we're calling this model P is a new variable, and we're calling on our model function defined up here, which is our Antoine equation solving for the log base pressure, log base 10 pressure. So our model is using variables x0, x1, x2, and temperature. And then we have our error is equal to jax numpy dot sum, which will add up the contents of these parentheses, and inside the parentheses we're going to have our model p. It'll be the difference between our model p and our log p, and then we want to square this value. So what this function will be doing is calculating the model based on these guesses, and then finding the difference between the model and the log of pressure data, the data point data, the difference between our model and the data points, square that difference, and sum all of the errors together. That's what this function is doing right here. So we'll have it return our error function. And now we want to, let's see if this works. And there's no error there, so we can do res, which would be our result to see how close we are to this fitting. Res is equal to our minimize function of the square error variable function that we define up here. We want to do this across x values from our guess, and then we want to replace our guess each time to minimize the function, and then give the resulting a, b, and c values that result. The arguments associated with this will include temperature and our log pressure. That's the same up here, but we are including our guesses out here, so that would leave just the temperature and the log pressure. And then we want to set a tolerance, so this will be telling Python how close the data points in the model must be to each other for this operation to be considered successful. So to start, we'll say 1 times 10 to the negative 10. The differences between the two, the model and the set of data, can be at most 1 times 10 to the negative 10. So here we go. Try that again and see what our result is equal to. As you can see here, this is the difference between our function, the result of our minimized square root error. We have a difference of 0.0005, which does not fall within this tolerance limit because we're getting a failure indication, and we're having these as our 3 variables, A, B, C. So if I reduce the precision limit here, let's say to the -7, we can see if we're still calculating false, and the variables had hardly changed, so I'll go down again. And now you can see when I've allowed for slightly more error, we have error of 1 times 10 to the -6 for a difference between our two our function and our data points. Now we are getting a true statement, and it is calculating these values for our A, B, and C constants of water within this temperature range that we have set. So I can change these however I want. I can multiply them all by 10 within reason, and this should still calculate it, and we're still getting true, and we're still getting the same values here with about the same result. Optimization terminated successfully. We made it within the tolerance limit. So now we have our model set up, and we have the data points on our plot. So all that's left to do is add our model to the plot. And to do that, we are going to, what did I just do? To do that, we are going to set a new temperature variable. We have T for our model is equal to, Jack's NumPy has a function called linspace, where it will create a number of data points between two limits evenly spaced apart. We can set the number of points that are evenly spaced between two limits. So we have our T0 is our first temperature entry, is the low end of our limit. Then we have T -1 is going to be the final temperature entry from our data collected, and we want to set this to have 100 data points. So this will be our x variable when we go to plot our model, or add our model to our subplot. And here we go. Fig dot add scatter. We want to add x is equal to T model. We have our y is equal to, it'll be our result function here, evaluated at x for all values within T model. So this is creating a scatter plot with this T model as all of our x variables, and then it is solving for the pressure at each of these temperature variables given the model that we've developed, and these as this A, B, and C constant for water's Antoine equation. In addition to this, we're going to want to make this a line to display our model, and we're going to name it. I forgot to add the quotations. All right, and then okay, so this is not looking right. Our scale has changed drastically, and this should be working. Give me a second so I can scour through this. So I neglected to give our function in here. So we have our model evaluated for our x's from the res solution. We take the x values, A, B, and C, and our temperature model temperatures in the Antoine equation to produce our plot. Alright, so we can save this and restart it because I had thrown the scale off drastically with this right here. Restarting our runtime will allow us to re-enter all of our data. We have to go from the beginning and input all of this again. So that initial plot is still working as we had set it up before. Our result function is still working as it had before. Now let's hope this is working better than before. And as you can see, our data fits through every single point that we pulled from the Dortmund data bank. And this program demonstrates the accuracy of the Antoine equation. This equation is phenomenally accurate through the temperature ranges it can be applied to for calculating realistic vapor pressures or temperatures given the other variable. And using a fairly basic minimization technique, we were able to fit this model within 1 times 10 to the negative 6, a tolerance of 1 times 10 to the negative 6. So it's a very accurate model representation. Thanks for joining me for this, and I'll see you next time.